Okay. Good morning to all of you. I welcomes to all in our lecture series on statistical mechanics. That is your core paper 14 belongs to 6th semester BSc syllabus. In our last class we have been discussed in detail about Wien's displacement law and its proof. Actually last class we have been discussed in detail about the proof of the Wien's displacement law. So these are the content whatever we have been discussed. Three important figures we have been discussed in that class. This is the another second figure and this is your third figure, and we found that your lambda t equal to constant, that is your Wien's displacement law. In today class we are going to discuss Wien's distribution law. Okay, here Wien's distribution law or Wien's approximation, it is also called as Wien's approximation, okay, is used to explain the spectrum of thermal radiation emitted by black body. This law derived by Wilhelm Wien. Okay, uh, actually Wien given two laws. Wien's displacement law in 1800, in 1803 years back, 1890, 1893. You just check your note. Yeah, 1893 he given Wien's displacement law. After 3 years he given another law, that is your Wien's distribution law, which explain the spectrum of a thermal radiation emitted by black body in 1900, sorry, in 1896. From the figure, from this figure, it can be found that the energy is not uniformly distributed in the spectrum of thermal radiation of the black body. What in this figure already we have been discussed when we discussed the Wien's displacement law with different temperatures here, and that time also we discussed that for each and every lambda the energy value is not same, so it is different. The energy intensity, the energy intensity is different. These things already we have been discussed. Here we are considered only one curve instead of all curve. We have been considered only one curve, and y-axis represents the intensity, and x-axis represents the variation of lambda, and this is your typical variation according to Wien's law. Okay, at particular temperature T. That means with variation of your lambda, with the variation of lambda, energy also varies, and at particular lambda it is maximum, above that, below that it is decreasing, right? These things we have been already discussed, right? Now here from the figure, one of the curve at temperature T, here we have been we are going to be discussed. Okay, from the figure, this figure, it can be found that the energy is not uniform. Energy, or you can say energy density or energy intensity. See, energy if I am going to consider this is your black body, and the energy is emitting throughout the surface, then we can say the total energy. If we are going to be consider from a particular volume it is radiating energy, then we can say the energy density, like that. So so E lambda is nothing but your energy is energy which is not uniform in the spectrum. Here spectrum means we are going to consider each and every wavelength is belongs to one spectrum. Okay, that you just remember. If we are going to put a going to consider the prism, and we have to a sun ray is going to be incident, then it will be dispersed with different spectrums. Okay, the or you hear one word, that visible spectrum. Visible spectrum means like this: red, green, blue, basic three colors we are considering always. Basic, our basic spectrum, that is your red and green and blue. Okay, so this side wavelength is decreasing and this side is your wavelength is increasing. This is the basic what spectrum that we know, and also spectrum word you have been heard at the time of your Balmora series, Paschen series, at the time of Bohr's atomic model. Okay, so each and every wavelength representing its own spectrum, but for each and every wavelength not having the uniform or energy equal, not uniform energy, it is different. That this line has been uh, here, that line, what it is meaning. Okay, next. Now, according to this law, the amount of thermal energy contained in the spectral region from wavelength lambda to lambda plus d lambda, suppose that is E lambda d lambda, emitted by a black body at temperature T, is given by an expression E lambda d lambda equal to A by lambda to the power 5 function of lambda t into d lambda. Okay, so what is the meaning of this? According to this law, means according to Wien's distribution law, if we are going to consider a very small range of wavelength, then the energy is going to be emitted with this much wavelength range, or you can say this area represents the energy, okay, which is in between lambda and lambda plus d lambda. In our last class, whenever we have been discussed Wien's displacement law, at that time we are discussed that uh, total amount of radiation energy increases as the area under the curve corresponding to increases. And here I have been discussed area under the curve represents the total energy emitted. So if we are going to consider a small strip which is in between lambda and lambda plus d lambda, then what will be the energy? That energy value will be represented by E lambda d lambda will be equal to A is a constant lambda to the power 5 F function of lambda t and d lambda. Here the term on the left side, that is your E lambda d lambda, is also called the spectral energy density. That I told that if we are going to consider from unit volume the energy is radiating in between this lambda and d lambda, then it will be called as the energy density. So E lambda d lambda is also called as the spectral energy density between lambda and lambda plus d lambda range. A is any constant and F lambda t is the function of the product of lambda t. Okay, so again Wien's distribution law can also be represented in the form of E lambda d lambda equal to a constant. Suppose this is your A dash T to the power 5. T is the absolute temperature of that body, function of lambda t into d lambda. Okay, now we have to start the derivation to prove these two expressions, this one and this one. Okay, so we know that emissive power E lambda is directly proportional to the energy density. So if energy density will be more, then emissivity will be more, right? That you just imagine that suppose we are going to consider a spherical volume. Inside this volume radiations are present, okay, photons, radiations, thermal radiations are present. So if energy per unit volume will be more, or the photons per unit volume will be more, then the radiation from this whole spherical cavity also is going to be more. That means the pressure on this wall will be more. Anyway you can give the language. That means if energy density, that means energy per unit volume, suppose this cavity or enclosure filled with the radiations, or you can say that the photons. Now we are going to consider a unit volume. If in this unit volume the number of photons will be increased, then the radiation from this cavity will be more. So here emissive power E lambda, it is represents the black body and its corresponding emissive power at particular wavelength is directly proportional to the energy density. So hence E lambda D lambda can be written as U lambda and D lambda, because energy density is nothing but your U lambda, represented by U lambda, that we know, where U lambda is the energy density corresponding to the wavelength lambda. Now we consider the radiations lying between lambda and lambda plus d lambda. Here this is the expression for a particular wavelength. Now we are going to consider the range that lambda and d lambda. In this range, whatever the wavelength we have to consider, from that wavelength what will be the total energy is going to be radiated. Now we have to consider thermal radiations lying in between lambda and lambda plus d lambda in the enclosure having the volume B. Okay, so the radiations present inside this volume or inside this enclosure having different type of wavelengths. So if we are going to draw the wavelength and its corresponding energy, then it will be like this. That blah blah, all the things regarding Wien's displacement law already we have been studied, and lambda t will be constant. Lambda is the particular wavelength where the energy intensity will be maximum, and corresponding to these things we have discussed. So here we consider a volume V in which enclosure having the volume V in which the radiations are present. Okay, and we are considering the radiation in between lambda and lambda plus d lambda. Then the total internal energy will be this much. So total internal energy, if we are going to represent U, then it will be energy density into V, total volume. The energy density is nothing but U lambda d lambda. U lambda is the energy density for a particular wavelength, d lambda is the range of the wavelength, and V is the total volume. So this is represents your total energy contained inside the enclosure. So the total internal energy of the inside the enclosure will be equal to U lambda d lambda into V, where U lambda d lambda is the energy density of the radiation. Here just radiation having wavelength range lambda to lambda plus d lambda. Okay, so here simply I explained here, for particular wavelength the energy density is U lambda. For d lambda range, if we are going to consider, then it will be U lambda d lambda for whole volume into V. That's it. So during adiabatic expansions, and we have to here consider the adiabatic expansion, whatever we have been considered in a radiation pressure, because some expressions we are going to be used from the radiation pressure. Okay, so if we are going to consider the adiabatic process, then this photons is going to be strike with this wall, and the wall is moving or enlarging its radius continuously due to the pressure exerted by the radiation. This concept already we have been discussed in our previous class. So here same situation we are going to be consider during adiabatic expansion. Now, if we are going to consider radiations are inside this volume, then due to the pressure this enclosure is going to be expand. Okay, but whatever the energy inside this, it will be constant. This means here we consider purely adiabatic process. So for adiabatic expansion of radiation, the work done in the adiabatic expansion will be dW equal to PdV. And for adiabatic expansion, we know that dQ equal to 0. There is no heat is going to be absorbed, and there is no exchange of energy. There is no exchange of heat. That means not taken outside, not given towards the outside. Thus, by first law of thermodynamics, the change in internal energy du can be written as du equal to dq minus dw. As here we considered the adiabatic process, the du will be equal to 0 minus p dv, because dw is nothing but p dv, and du equal to minus, here p is your radiation pressure, that is nothing but your, for diffuse radiation it is your p equal to one third of energy density, one third of energy density. So energy for a particular wavelength, this is your u lambda, but for a range of wavelength here we have been considered, no, so it will be u lambda and d lambda. So for the diffuse radiation, p will be one third of u lambda d lambda into dv. Okay, we have to go for the next page. Now we have to move for the next page. Okay, so here instead of u we can write capital U, we can write u lambda d lambda into v. Okay, so d of u lambda d lambda v equal to, right hand side it is 1 by 3 u lambda d lambda v. Okay, so it will be minus 1 by 3 u lambda d lambda into v. So that implies, here you can see three functions are there. We are going to be consider the product formula for the derivative. Let first we have to do the derivative of this one. So it will be d square lambda, and these are not going to be, these are will be act as the constant. Simple product formula. So here du d lambda d v, and again derivative of v. So these are going to be not going to change anything. So u lambda d lambda into dv will be equal to, here 1 by 3 u lambda d lambda into dv. Okay, this is dv. Now we have to divide u lambda d lambda v both the side. What we are going to get? See here, u lambda d lambda v with the first term. Second term also we have to divide u lambda d lambda v, plus we have to divide u lambda d lambda v with the third term, and the right hand side also we are going to divide u lambda d lambda v, and the numerator is the u lambda d lambda v. See here, u lambda is the subscript, lambda is in the subscript. Okay, now here you can see that u lambda got cancel, v got cancel. So here it will be only d square lambda by d lambda. It can be written as d of d lambda by d lambda, and here d lambda v got cancelled, du lambda by u lambda, and here you can see this will be u lambda d lambda got cancelled, and we found dv by v. So dv by v will be moved to the right hand side, it will be minus dv by v, and from here we can get u lambda d lambda got cancelled, and it will be minus 1 by 3 dv by v. So here minus 1 by 3 dv by v, and this term gone to this side, it will be minus dv by v, and this two term is going to be add up, and we are going to get minus 4 by 3 dv by v. Okay, but d of d lambda by d lambda is nothing but d lambda by lambda. It is we know that this one. So instead of this one, we have to write d lambda by lambda plus du lambda by u lambda equal to minus 4 d lambda by lambda, because dv by v equal to 3 lambda by lambda. This things already we discussed. You just check your note in your radiation pressure. Okay, in your radiation pressure, here you can see that if we are going to consider the volume of this sphere, volume of the sphere having the radius is r, then the volume will be 4 by 3 pi r cube, taking log both the side, blah blah, we can get d delta lambda by lambda equal to 1 by 3 delta v by v, or d lambda by lambda equal to 1 by 3 dv by v. So same thing we have been all directly here we have been substituted. Okay, so instead of dv by v, if we are going to be put 3 d lambda by lambda, so 3 is going to be cancelled out, and we are going to get this is 3. Okay, we are going to get minus 4 d lambda by lambda. Okay, previously we found. Okay, now d u lambda by u lambda will be equal to this d lambda by lambda taken this side, it will be add up with this one, it will be minus 5 d lambda by lambda. Right, now we have to integrate both the side, so it will be ln u lambda will be equal to minus 5 ln lambda plus ln some constant. Okay, so take this side, this one, this side. Okay, see here, 5 ln lambda can be written as ln lambda to the power 5. Here minus is there, taken this side, it will be plus ln lambda to the power 5 equal to ln constant. Right, so this will be written as this one, this two term can be written as ln u lambda into lambda to the power 5 equal to ln constant. Right, so u lambda lambda to the power 5 will be constant. Okay, so u lambda lambda to the power 5 will be a constant. Now the equation number 1 will be, where is the equation number 1? Here, equation number 1, d e lambda d lambda u lambda d lambda. So here we found that u lambda lambda to the power 5 is constant. Right, so here from this, how much we can get the u lambda? U lambda will be constant by lambda to the power 5. Now we have to just substitute this u lambda in your equation number 1. Equation number 1 is your e lambda d lambda equal to u lambda d lambda. Here we have to put, instead of u lambda, this value. Then what we can get? E lambda d lambda equal to constant by lambda to the power 5 into d lambda. Right, but according to Wien's displacement law, this is your lambda t equal to constant. That means constant is nothing but your lambda t. Right, now this constant has been written a, this constant can be written as another constant with multiplication of lambda into t. Right, okay, because lambda t is itself a constant, so this constant can be written in the form of a, which is a constant, and function of lambda t. Okay, so hence this constant has been rewritten in the form of a into function of lambda t. This here this is the function of lambda t, means lambda into t. We have to, if we are going to multiply, then it will be, this value will be a constant. Right, so here we found e lambda d lambda equal to a by lambda to the power 5 into f of function of lambda t into d lambda. This is your equation number 2, and hence also it is proved. We derived our first expression. Right, this is your first expression, that is e lambda d lambda equal to a by lambda to the power 5 function of lambda t into d lambda. The second expression is that e lambda d lambda equal to a dash t to the power 5 f of lambda t into d lambda. That we have to be derived from here. It is very easy. We get u lambda to the power 5 equal to constant. Right, now u lambda is equal to constant by lambda to the power 5, but according to Wien's displacement law, lambda t equal to constant. Right, so lambda t to the power 5 equal to constant, so lambda to the power 5 will be constant by t to the power 5. So hence if we are going to consider 1 by lambda to the power 5, then it will be just reverse t to the power 5 into constant. Okay, see here, if we are going to take that reverse, that t 1 by lambda to the power 5, here 1 by this much, then it will be t to the power 5, and 1 by this constant itself a constant. Right, now equation number 2 will be See, equation number 2. Now we have to put the values. Now in the equation number 2, then what it will be? Instead of lambda to the power 5, what we are going to be put? Instead of lambda to the power 5, if we are going to be put, sorry, instead of 1 by lambda to the power 5, here it is 1 by lambda to the power 5. So here we have to just put 1 by lambda to the power 5 value. So it will be E lambda d lambda equal to a into 1 by lambda to the power 5 is nothing but t to the power 5 into constant. T to the power 5 into constant f of lambda t d lambda. So here a is the constant, another constant, suppose it is a dash f of lambda t into d lambda t to the power 5. So this is the another expression of your Wien's distribution law. So this is all about your derivation of this Wien's distribution law. So I suggest watch the video carefully, write down the note and ready for the next class. Next class we are going to be discuss another important topic, that is your Rayleigh's law. Okay, thank you so much for watching this video. Thank you.